Let's talk about a real head-scratcher, a mystery that sits right at the intersection of biology and physics. It's this. Why is it that as brains get bigger, they actually get more energy efficient? It's a total paradox that seems to fly in the face of everything we think we know, and it's had scientists stumped for a long, long time. And, this isn't just some dusty old academic question. It really gets to the heart of how incredibly complex things, like us, evolve when you're on a tight energy budget. The normal rules of efficiency that we see all over nature, well, they just don't seem to apply to the brain in the same way.
I mean, you'd think, right? A bigger brain, billions more neurons, it should just be a bigger, more gas-guzzling engine. It should consume proportionally more power. But that's not what happens. Not at all. Something way more fundamental is going on under the hood.
To really see what I mean, let's look at two extremes. You've got the tiny little brain of a mouse, and then you've got the absolutely massive brain of an elephant. Now, here's the crazy part. On a per-neuron basis, that elephant's brain is just sipping energy, while the mouse's brain is chugging it down like there's no tomorrow. How is that even possible?
Well, the first clue is actually surprisingly simple when you look at it. It turns out that, on average, a single neuron in a small brain is way busier. It's firing way more often than a neuron in a large brain. So it's not just about how many neurons you have, it's about how hard each one is working on average.
Okay, so to really crack this case, we've got to look at another piece of the puzzle. The brain's unbelievable, nonstop hunger for energy, even when it seems like it's not really doing anything at all.
Your brain is an absolute energy hog. It's the most power-hungry organ you've got. And what's wild is that even when you're just resting, not thinking about much of anything, its fuel consumption only drops by about half. It is always on, and it is always hungry.
And Dr. Timothy Ryan really nails it with this quote. The brain's machinery is burning fuel even when it's just idle, waiting for something to happen. So why? What's causing this constant background drain?
Well, it all comes down to something you could call a leaky synapse. So here's the deal. All the brain's chemical messengers, they're stored in these tiny little bubbles called vesicles. But these bubbles aren't perfect. They have this constant tiny energy leak. And to fight that leak, a little molecular pump has to run 24/7, just burning fuel to keep them topped up and ready to go.
So, okay, let's recap. We've got two big clues, this constant energy leak and this weird efficiency we see in bigger brains. And it turns out nature is actually full of these kinds of surprising efficiency rules. We call them scaling laws.
The fancy science term for this is allometric scaling. But really, all it means is that as living things get bigger, their characteristics, everything from their shape to how much energy they use, change in a predictable mathematical way. It's a fundamental rule of biology.
Probably the most famous example is something called Kleiber's law. It basically says that as an animal gets bigger, its metabolism doesn't just scale up 1-to-1. Instead, it scales to the 3/4 power of its mass. In simple terms, bigger animals are just more fuel efficient. But the brain follows its own, even more dramatic special rule.
The brain's efficiency rule is totally unique, and the answer, amazingly, doesn't just come from biology. It's a stunning breakthrough that comes from the world of physics, and it points to something incredible happening inside our heads every single second.
And the core idea is something called a neuronal avalanche. It sounds complex, but it's really a beautiful, simple concept. Think of it like dominoes. When one neuron fires, it can trigger its neighbors, and they can trigger their neighbors, creating this chain reaction that ripples through the whole network.
So it all kicks off with just one little spark. One single neuron decides to fire and sends out a signal. But it's what happens next that changes everything. Because that one little spark, it could just fizzle out and die. Or it could trigger a small little ripple of activity. Or it could ignite a massive, brain-wide cascade of firing. The amazing thing is that the size of these avalanches isn't random. It follows a precise mathematical pattern.
So the theory is that the brain operates at what's called a critical point. Now to get this, just imagine building a sand pile, one grain of sand at a time. It gets steeper and steeper until it reaches this perfect angle. That's the critical point, because at that moment, the very next grain you drop could cause just a tiny trickle, or it could trigger a massive, catastrophic landslide. The theory is the brain is balanced on that exact same knife's edge.
Okay, this avalanche criticality idea. It's a beautiful theory, right? It sounds great. But in science, a cool idea isn't enough. You have to be able to test it. So the real question is, how can we be sure it's actually true?
Well, a good theory has to make a specific, testable prediction. And this one does. It says, if the brain really works like a critical sandpile, then as the brain gets bigger, its total firing activity should increase much more slowly than its size. It has to follow a very specific mathematical curve. And what do you know? The proof is in the pudding. When scientists ran computer simulations of these neural networks tuned to that exact critical point, the results were a perfect match. You're looking at the graph from the paper right here, and it shows that as the number of neurons grows, the firing rate scales exactly the way the theory said it would. And here is the part that will absolutely blow your mind. This isn't just some special rule for brains. The exact same mathematical law also describes the activity in a simple computer model of a sandpile. This isn't biology we're talking about anymore. It's a universal law of physics that applies to any system that's balanced at this critical point.
So what does this universal physics principle actually mean for real, living brains like ours? Let's connect the theory back to the biological facts on the ground. The theory predicts that the individual neurons in bigger brains should be lazier, and that is exactly what we see in the real world. Real-world data shows the average firing rate for a neuron in a rat's cortex is about 4.3 times a second, but in our much, much larger human cortex, it's only about 1.15 times per second. The theory holds up.
So, the big takeaway here is this. The amazing energy efficiency of bigger brains isn't some special feature that evolution had to painstakingly design. It's what we call an emergent property. It's just a natural consequence of a complex network organizing itself at this critical tipping point. In other words, for a big brain, being efficient isn't the exception, it's the rule.
And this leaves us with just a huge, fascinating final question. If this principle of avalanche criticality is what governs the efficiency of brains, where else is this hidden rule at work? Could the same law of physics be shaping the dynamics of our economies, the stability of our ecosystems, or maybe even how information spreads online? The brain might just be the most amazing example of a truly universal law of nature.